Hey everyone, so in this video what I want to do is do a couple of examples on solving systems of equations, uh, 2 by 2, 2 dimensions basically, and through the use of matrices instead of just the traditional um, substitution method and elimination methods. And you'll see the power that matrices possess because they can help us simplify so many things in so many different ways, and it's just really it's an important skill set to have if you're solving a large system of equations. So basically, what is a system of equations? You know, if I have something like ax plus by is equal to some constant c, then I have another equation dx plus ey is equal to f, right? This right here is an example of a system of equations. Now, this is a linear system of equations, there's no quadratic terms, and we'll only be dealing with linear terms most of the times anyways. So, linear terms, how many unknowns do I have? I have two unknowns, x and y. How many equations do I have? I have this first one over here, and then the second one over here. So I have two equations and two unknowns, okay? Now, for something small, like two equations and two unknowns, we can just use something like substitution or uh, elimination, right? So substitution. I'm pretty sure I'm spelling it wrong. substitution. I think it's right, but I don't know. It might be wrong. Whatever. So one method is substitution. The other method is elimination, right? So we can simply do that. You know, find the common coefficient, subtract one from one equation from the other one, get rid of the x's or the y's, and then just easy peasy from there. The thing is, if I have if I have 10 equations and 10 unknowns, do you see the problem that can happen if I'm going through substitution or elimination, and not just 10 10 unknown 10 equation kind of problem. Even if I have just 3 equations and 3 unknowns, like if I have ax plus by plus cz equals d, and keep on going like that, and whatever, I have a1x plus b2y plus c2z is equal to d2, right? I mean, if I have 3 equations and 3 unknowns, I'm gonna have a lot of trouble if I'm just gonna do substitution and elimination each time, right? It's still not that bad for a 3 by 3, but you know, if the numbers aren't that good, elimination can be a hassle. I have to keep tracks of all the things that I'm multiplying the equations by, and it just becomes a time-consuming process. So that's where matrices and equations uh, can come into place. So what I'll do is, this is known as the AX equals B method. So basically it's the matrix A times the vector x. Now it's important to know that x is a vector. So if you're looking in a textbook, it'll probably be a bolded x is equal to b. Now b is also a vector, but you know, sometimes you won't see it. It's a bolded out b. Okay. So what this basically does is I want to take this right here and use matrices instead of just elimination to solve for it. Okay, and the way we do that is we let A be the coefficient matrix. X vector will be the vector of unknowns. So I'm just gonna say, and if you don't know what vectors are, um, then you know, I would assume you'll take the time to learn them after this video. But it's not super important that you know what vectors are. Just if you follow along the logic, then you'll be fine. So vector of unknowns, unknowns, and then the b is the answer, or not really the answer, but just like um, just the c and the f. So basically, what they're equal to, what is equal to. Okay, so the way I do that is I look at the coefficients. So what's the coefficient of the term x over here? It's a, right? So I'll put a here. What's the coefficient of the y term here? It's b, positive b. What's the coefficient of the dx over here? It's d. What's the coefficient of ey? It's e. Alright? To that, I'm going to multiply it by the x thing, which is my unknowns. Well, what are my unknowns? Well, one of my unknowns is x. The other unknown is y, right? That's what I'm trying to solve for. So x and y. And what's that equal to? Well, what is equal to? That's c over here and f over here. Now, do you see the helpfulness of this? Well, are these two things equal to each other? The way we can prove that is just perform the matrix multiplication. What's the dimension of this matrix over here? It's 2 by 2. What's the dimension of this matrix? It's 2 by 1. Can I multiply them together? Yes, the inside two numbers are the same. What will be my resulting matrix? Resulting matrix dimensions, it'll be 2 by 1. So what's the answer? So it's ax plus by, the dot product of the first row with the first column. Right? So I'll get ax plus by. Alright? And then what's the other one? So dx plus ey. And what's that equal to? Well, that's equal to c, and that's equal to f. Okay? So yeah, these two are exactly the same thing. Okay? The only thing now is that this right here is in the form of matrices. So let's hop on over to the next slide, and we'll actually solve an example of this. So in this example, let's say I have some matrix, or let's say I have a system of equations. I have 2x plus 3y is equal to 0, and then x minus y is equal to 5. Okay, I just made these values up, but we'll see if they work. So how can I solve this using the ax plus b, or ax equals b, right? So, method. So ax equals b. Right, in this case, I have my coefficient matrix A, so A is equal to what? All the coefficients. It'll be 2 over here, 3 over here, 1 over here, and then negative 1 over here, right? And what's my x? X is the vector of unknowns, okay? It doesn't necessarily, this x over here and this x over here are not related at all, okay? I could have unknowns of a and b. If I had a is equal to x and y is equal to b over here, but that's not the case over here. So we'll just stick to the convention. So this will be x over here and y over here, okay? And what's my b? Well, b is equal to 0, 5. Okay. So how do we solve this? We can set this up in this form over here, and we'll get 2, 3, 1, negative 1 times xy is equal to 0, 5. Remember, back in the inverse video, we said that if we figure out the inverse of a matrix and we multiply that matrix by its inverse, okay, we will get the identity matrix. And this is where the power of the identity matrix comes in. Okay, so the identity matrix acts as a 1. Basically, I had that example, 5x plus 10 is equal to negative 5, or I had positive 5, but I'll just use negative 5 over here, doesn't matter. And then I have 5x is equal to negative 15 because I take away 10 from both sides. And in order to get the x by itself, I need the inverse of 5, which will get me x is equal to negative 15 over 5, which is equal to negative 3. So in this case, our x is the xy over here. We need to get that by itself. We can't just divide by matrices, so we need to figure out the inverse. So in this case, A inverse is equal to 1 over the determinant. What's the determinant? Well, it's a negative 2 minus 3, right? So negative 5. Then we switch it, negative 1, 2, this becomes a negative 3, this becomes a negative 1, right? So that's A inverse. So now what I do is I multiply both sides of this equation by A inverse. Okay, which in turn will get rid of the 2, 3, 1, negative 1. Okay, so when I do that, I get, I'm just going to write this A instead of this whole matrix. So I'll have A inverse times A times the x vector, which will be xy, is equal to, now if I'm multiplying it on this side, I'm going to multiply it on this side as well, right? So A inverse times 0, 5. Now it's important I don't do 0, 5 A inverse, because that's not the same thing. A inverse will have dimensions of 2 by 2. This matrix over here has dimensions of 2 by 1, right? So I can't multiply them together. Remember, AB is not equal to BA most of the times, right? In this case, this is one of the prime examples of it. So I have to do A inverse times 0, 5 because the dimensions match up. This is a 2 by 2, this is a 2 by 1, so my resulting value would be a 2 by 1, okay? So now when I do this, A inverse times A will just be the identity matrix. This will be I2 times the x vector, which is the unknowns, x and y. This will be equal to A inverse times 0, 5. Okay, so A inverse is equal to negative 1/5 times the negative 1, right? So A inverse is equal to 1/5, 3/5, 1/5, and negative 2/5, right? And now to that I'm multiplying the c, which is a 0 and the 5 on the right hand side, right? So 0 and 5. And what's the resulting matrix? Well, it'll be 2 by 1. So it'll be 1/5, 0, so it'll be 0 plus 3, so this will be 3. And then this will be 0 minus 2, so this will be minus 2. Okay, so this right here is a solution of our matrix. Why? Because this right here acts as a 1, right? And then 1 times anything is just that anything. So x vector, which will be the unknown, xy, is equal to 3, negative 2. And so x is equal to 3. So I'm just going to write this here. X is equal to 3, and y is equal to negative 2. Okay, so if I plug it in this equation over here, does this work out? Well, x is 3, so this will be 3 minus negative 2 is equal to 5. Okay, yeah, that works. Over here, what about over here? So it'll be 2 times 3, so it'll be 6, plus 3 times negative 2, which is negative 6, which is equal to 0. So yeah, that works. So the power is we can use systems of equations, okay, convert them into matrices, and then go on from there by taking the inverse, multiplying the inverse to both sides of the equation, forming the right order of multiplication on the right hand side, and then we get the answer. You might not see the value of it in just using 2 by 2s because it's probably simpler if I just solve this system of equations using just normal methods like elimination. But with even something such as like a 3 by 3 or a 4 by 4, it becomes really simple if you're trying to use this matrix method instead of just elimination or substitution. So that's it for this video. We'll go on to the next one. Hope you like this one. Good luck.